Hi everyone, welcome to today's session on linear algebra to geometry. Let's start in 5 minutes so that others can join. So, hi everyone, welcome to today's session. Let's start the meeting. Mm, Is my screen visible, everyone? Anyone, can you confirm? Great. So, let me know if you face any difficulties during the session, right? So, for today's session, what we did is we finished up the week 7 plus week 8 problems, right? Fine. And then, okay. So can anyone remind me, did we cover this week 8 notes? Did we start anything related to week 8?
No, sir, not the notes. We have just finished week 7 problems. So I
Hmm.
don't think that we have started week 8 notes.
Okay. So we just finished this week's 7 remaining problems, right?
Yeah, yes, sir. Yeah.
Okay. Fine. So let's start with the some brief review of what has been taught in the previous session, and then we will start with the problems. Fine. So yeah. So essentially, what in week 8, what was taught is generalization of vector spaces to a general M cross and dimensional spaces, right? So till now, what you are seeing is only 2 matrices or 3 cross 3 matrices. From now onwards, we will not limit ourselves to do these 2 cross 2 and 3 cross 3 matrices. We will generalize to M cross and general M cross and matrices. Fine. So we will see how the properties that are observed in 2 cross 2 plus and as well as 3 by 3 matrices will extend to M cross and general matrices also, right? So you will see that similar behavior for all the properties and theorems that we saw for on all these kind of general matrices also. Fine. So let's start. Hmm. So a vector space defined over Rn. So as a non is a non-empty set of vectors with operations, vector addition, and a scalar multiplication. So this is essentially a definition of n-dimensional vector space. So the definition of a vector space is it is a non-empty set that contains vectors over which some operations are defined. The operations are vector addition and scalar multiplication. Now, if you consider such vector space, right, you can see these properties will always hold for any vector space. So there are total 10 properties here that I have covered. This has been covered in the lectures also. So these properties will always hold if you are defining a vector space, right? So basically, if U and V belongs to V, right? If if u comma v both belong to vector space V, then u plus v also belong to v, then alpha into u, basically alpha is a scalar vector product will also be in u, so basically it's closed under addition and closed under scalar multiplication. Then this is u plus v equals to v plus u, basically commutative under addition. Then associativity property will hold. Then let's say you have another vector w, then you can see that u plus bracket v plus w is equals to u plus v plus w. So this is associative property, right? Then there is exist a zero. So basically this is additive identity, which is zero. So u plus zero equals to u. Whenever you talk about identity operation, it is something that u into some operation over some other variable v. And if you talk about identity, it is u into some other variable v is essentially u. This is identity. So zero exists for vector spaces, zero vector. Inverse also exists for vector addition. So u plus minus u is equals to zero. So inverse exists. Then alpha, again, this is distributive property for scalar vector product, a scalar product with a vector add sum, right? Then, right, this is again distributive property here. And then this is associativity. So basically, scalar product associativity. This is if you're multiplying with two scalars, that you can associate them, right? Then multiplicative identity I1 in exists, right, for vector spaces. So, so basically, there is one scalar product, a scalar value one multiplied by VU will always give you U, right? One thing you have to note that is in vector spaces, can't see any inverse of U, right? You can't see something U inverse because this is not defined for vector spaces, for vectors essentially, right? And there are some examples. Any line that passes through the origin is a vector space. Any plane passing through the origin is a vector place. Why? Why it has to pass through origin? Because of the properties 5, 6, because of the properties 5 and 6, right? You need to have 0 in your vector space as well as an inverse should exist. So u minus u has to be 0, additive inverse basically. Fine. U minus u equals to 0. So basically 0 has to exist. That's why the plane or the line has to pass through the origin, right? So this was basics on vector spaces. Then vector subspace, any subset of W of a vector space, any subset W, let's say we choose a subset of vector space V, which itself is a vector space, is called as a vector subspace, right? For example, let's say, what can we say? Let's say, so basically the Venn diagram looks like this. So let's say you have this vector space V, then and you define another vector space W here. So if W satisfies all the properties of a vector space, then W is uh, a vector subset of vector subspace. Basically, it is known as vector subspace, a new term, right? Now, zero, a trivial subspace of V is origin, right? Origin is a subset of any vector space and it exists in V, so it is a trivial subspace. Then union of two vector subspaces are subspaces if and only if one of the subspace is subset of other subspace. Then only this is possible. If it's not true, then it's not possible. So the union operation between two subspaces is only possible if one of them is subspace of another one, right? And intersection is always a subspace. Intersection of two subspaces is always a subspace. And complement is never a subspace, right? Complement will never be a subspace. Right? Any doubts in these? Any doubts in the properties of vector spaces and vector subspaces? And we are not talking about two by two-dimensional or three-dimensional spaces. We are dealing with n-dimensional, general n-dimensional spaces. Yeah.
Sir, one small doubt. In vector subspace, the first property that union is a subspace. You said only if, right? The if and only if
Mhm.
one of the subspace is contained in another. So actually,
Hmm.
there was a similar question in assignment. The due date is over. So and in the question, there was a little bit of problem. Like the question itself says W1 is not a subset of W2. The given conditions. Let's say
Hmm.
W1 was
Okay.
defined there. W1 equal to span of some two vectors that were given, and W1 was not
Hmm.
a subspace of W2 in that case. And in the
Hmm.
options
Hmm.
that were given, one of the options were the union will be a subspace only if that condition. So in
Hmm.
that scenario, is it a correct option or
It's
yeah,
contradicting, right?
right?
The problem statement says it's not a subset, and then the option is saying it will be subspace only if it is a subset, right? That's what you are saying, right?
Right, right, right. So with the given data, it is not a subspace. But the problem, if someone says that the problem statement is independent of the fact whatever is given, they are saying W1 union W2 is a subspace only if this scenario happens, and that is a true statement. That's why my doubt comes in.
Okay.
And one more thing, is it a only if condition? And can you help me visualize why it is a only if? Like there can't be any possible scenario in which the union could be a subspace.
Okay, fine. So the first thing, essentially, when it is saying it is a subspace only if U is a subset of W and W is a subset of U, then this is some independent statement. It does not require you the definition of U and W. If one of them is a subset of another, then it the union will be a subspace. That's it. Now, if the question in the question, if it is not a subset, it's not the problem. The problem is they are essentially talking about general subsets. So yeah, the answer is correct in a way, but I'm still not happy with the. I mean, I still doubt what's the use case of giving the span. Then I don't know. I mean,
Yeah,
yeah.
right. So, sir, actually, after this class, if you have some time, like after solving those problems which you have taken, can you just have a look at that
Hmm.
problem? Then it will be easier for me to tell you.
This is question two, right?
Yeah, I think so.
This is question number two. Span of this. Yeah, the option is correct, independent of the problem statement. That's what I'm saying. This will be always be true. Whatever you
No,
decide,
but
Q and
there
W.
is an option,
The
no?
the
There is
option is
also another option, which
hmm.
seems to which seemed correct to me that they are never a subspace kind of a thing. Is there an option like this that they are never
Ah,
subspace of
U
R4 or
union
something?
W is never a subspace, right?
Right. I pointed that because I found with a given problem statement, U and V are not becoming U union V. That thing is not becoming a subspace. So I clicked on that,
Hmm.
but while evaluating, they told that the correct statement is this. Yeah, one thing I messed up. I didn't think at that time that only if condition. So I was thinking maybe there might be some other cases possible as well under which union of two subspaces is a subspace.
Ah, wow, okay, but U union W when you talk about hmm. Okay, fine. Did they give any explanations for this?
No, only that accepted answer says U union W is a subspace only if this thing. The correct statement they have given accepted answer as. I have mailed them, but sir hasn't replied yet. I think he will reply. So, so in my understanding, I am seeing that in this problem, U union W is not a subspace because of failure of some closed properties and those things. Closure
Hmm.
is not there actually.
Yeah, right. Yeah.
So but yeah, if someone looks at it from a perspective that independent of the given problem, U union W is a subspace only if this thing is a true statement always. So by that, if someone
Hmm.
goes, so that's where my doubt is actually. So while clicking on this kind of problems, should I be looking at in general what happens or based on the given data?
I'm saying this thing that it if if you write any span, right, you can write any kind of span, and the option says this is true if this condition holds, and that condition is
Mhm.
a universal condition that if that condition is true, The property holds for any kind of input. In that case, you give any example, that statement will be true, right? In that case, if
Yes.
you choose any example, it will be true. So it doesn't matter if that is given or not. What I'm saying is, if I had to choose
Okay.
one option that is true, I'm sure that
Right.
second is always true. I will not even look at the problem statement.
Okay. But if someone clicks on the third based on the fact that it is not a subspace here with a given data, so is
I
he
said
wrong?
never a subspace. What is the meaning of never here?
Right. So it is quite ambiguous that never part is not a subspace is a like understandable thing from the
It's
given
not a
fact.
subspace, right? Yeah, I don't know. You can talk to them and then you get the answer.
Okay. Okay.
Fine.
Okay, sir. We can continue. Yeah.
Okay. Yeah. So this is it. Do you need any example on this property, anyone?
Uh, not. Can you give us some visualization why it is the only requirement criteria? Why can't suppose there is a disjoint part between them? Then why it fails to be a subspace? Like why it is always the case
Oh,
one should be contained in another?
let's see. We are talking about vector subspaces, right? So let's take this to 1, 0 and 0, 1, right? Let's take the very basic example in the Euclidean plane, right? You have to define two vector spaces. One, oh, sorry, one that passes through the x-axis, right? This is one vector space. Then another one that passes through the y-axis, right? Now, let's say what I'm doing is I'm taking a vector sum, right? Vector sum is defined for any subspace, any vector space, right? So I can do vector sum. So let's say I am doing the vector sum 1, 0 plus 0, 1, right? Now, this is essentially 1 comma 1, right? So this is the output of our vector space, vector sum over this vector space, union of these two, right? So basically by union, what I'm saying is any vector that is along the vector 1 comma 0. So k into 1 comma 0, k1 into 1 comma 0 and k2 into 0 comma 1 is the set that contains all the vectors in their union, right? Now, what I want to say here is, so we have a set that looks like this: k1 0 comma sorry, k1 1 comma 0, k2 0 comma 1, right? So this is our interesting interest set in which we are interested. This is the union of those two. Now my what I want to test is I want to test these 10 properties. Does this set satisfy these 10 properties over vector addition and scalar multiplication? And the property I want to evaluate is the closure over the first property. Is it closed? I just want to check this property if this is true or not, if this holds or not for this union, right? Now let's see. So I choose the first vector from this set 1, 0. I choose the second vector from this set 0, 1, right? You get the sum as 1, 1, right? Now does 1, 1 is 1, 1 in this set? Anyone?
No, no, no.
Fine. So basically, all the vectors on this line on the x-axis and all the vectors on y-axis belong to the set, belongs to the subspace. Then you are taking another vector 1 comma 1, which is here. The question is, is it lying in the subspace? Anyone? Rohan, you had the doubt, right?
No, sir. It is not lying. So here it is lacking the closure property. But I was saying that
Yeah.
why it will always happen. Like this is
Okay.
a particular example.
Mhm. It will always happen. Why? The question is why. Then the answer is okay. So think of it like this. let's say, let's think geometrically. So let's say I have a general vector v1 that goes like this and it forms a vector subspace. You have another general vector v2 that is not in the direction of v1, right? v2 is not equals to k times v1, right? Then what what I want to prove is ki, do they will they ever form a subspace or not, right? The question is this. Their union,
Uh,
right?
so
And
sorry
for
to interrupt.
union, yeah,
So this is not the exact question that I'm asking. So obviously, definitely,
yeah,
again, if you take v1 plus v2, it will not lie on the subspace. What I'm saying is
yeah.
that, so I have a two Venn diagram in my mind, which have a little
Hmm.
intersection part. Can you draw that?
Hmm.
Yeah, right. So the first one I'm thinking it is a vector space, not a set only. The first circle is a vector space, and the second circle is also a vector space, but one is not
Hmm.
contained in another, right? So in this, for this scenario, I want to see that V union W will not be a subspace.
Yeah. So that's what I'm saying. So let's take the first vector space as a set of vectors along V1. Let's take the second set as set of vectors along V2. Fine.
But they don't have any intersection part, no? Like they have only zero vector. So I'm thinking about some other
So
case where
that
they
is
have a
that
lot
is
of
an
intersection part.
intersection. That is an intersection, right? Okay, so
Only
you
zero
can
vector.
extend this to planes. Or you want to extend this to planes, then this is also possible. So let's say we have this
Okay.
plane,
Mhm.
and then we have this plane that crosses it like this, right? So this is the boundary, let's say. So this is the line, right? You can see this line where these both are meeting.
So line will pass through origin, right? Two planes are there
Yeah,
which are passing through origin.
right,
So
right.
line will pass through origin.
Uh, Basically, yeah, there will be origin. Let's forget about origin right now. I'm not
Okay, okay.
interested in the origin right now. But it is
Sure, sure.
important for it to be a space. But I'm just saying, if you ignore that property also, then also it does not satisfy that property. That's what I'm saying. How? That's what I'm trying to show. So let's ignore the coordinate axis. Assume that these are passing through the origin, right? So this was my first plane, and this is my second plane. Right? So these are my two planes, and they are cutting here, right? So this is the
Yes.
cutting point. So this will be a line. You will observe that along this line, the planes are intersecting, right? Now let's take a vector in this black plane. Let's take it from here. Let's assume this is the origin. Let's go from here to here. Take this vector, right? Now take another vector in the blue plane. So this from here to here, right? Now when you just check for the first property, closure property, is the sum of these two vectors does the sum of these two vectors lie on both of these planes? Can you tell me?
It is sum of two vectors, whether they lie on the two planes.
Sum of one vector which is lying in this black plane, another vector which is
Okay.
lying in the blue plane, non-zero vector obviously. If you add them
Mhm.
up, does the result lie on the both the planes?
Geometrically, I can think actually, but I'm having a little bit of problem. How do I write and how do I show that they do not lie in any of those planes? I can think, yeah, that they won't lie because, yeah, I can
Hmm.
visualize that they won't lie. But how can I write or how can I argument, prove someone that they do not lie on?
Okay. So let me write it. Let's say V1 defines a vector space and V2 defines a vector space. And I'm talking about V1 plus V2, right? And I'm talking about V1 lies along V1 as well as lies along V2, right?
Union P2 talking about, no?
U1 union V2, right? I'm talking about union. Right.
Union P2.
Let's start thinking. I'm saying, let's say I have a vector W and I'm saying it belongs to the space V1, right? Do we agree with this? Let's say this is a
Yes.
some statement I am saying W belongs to V1. then you can always say that W dot V1 has to be 0. Just think of vector spaces, vectors, right? First, just
Why the
talk
dot
about
product should be
vectors.
zero?
You are talking about a vector space, right?
Right,
And from that vector space, you are sampling one vector. And let's say that vector space is along a vector. Fine.
right. Yeah.
So, sorry, it's not 0. Okay, I'm wrong. It has to be 1, right? If it's a unit vector.
Oh, yeah, right.
Plain signal.
Or,
Plain signal. Okay, I think the better way would be using a plane. Let's use a plane here. And we have a normal defined for this plane. And let's say we choose a vector in this in this plane, right? Vector v. Then, and this is the normal vector. So you can always say v dot n cap is 0, right?
right.
Is this true? Fine.
Yes, yes.
Now let me choose another plane, the black plane here that goes like this, that cuts like this, right? It has its own normal. This was
Just
n1,
can
this
you
is
go
n
the
cap
earlier one?
2. Yeah,
Yeah, yes, sir. Yeah. What?
what? Fine.
No, 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 sir. Yeah.
Now,
Yes.
what is the doubt?
No, sir. I was also saying
No,
it as in yeah, the same thing. So now the doubt is like
yeah.
if
So
we take
this is the
one vector
property
from
that
blue plane.
we, hmm, right. What I'm saying is, let's say, let's call this space 1, and this is our space 2. And my claim is V is in space 1 if and only if V dot n cap 1 equals to 0. Do you agree with this?
Yes. Right.
Right? This is true.
Yes.
Now, what
Yeah.
we want to see is what happens if I take a vector V, which is in space 1. So let's say V belongs to S1, and let's take another vector W belongs to S2, right? Now, this means V comma W both belong to set S1 union S2. Do you agree with this?
Yes, sir.
Fine. Now, what I'm trying to check is the closure property over this. Now, if I do V plus W, right? And I'm saying
Yeah.
this should belong to the set S1 union S2. Is this true?
So that's what we are
Am
checking,
I
right?
right
We are
here?
trying to prove they won't belong.
Ha. What I'm saying is if this
Okay.
is true, then closure property is true and
Yeah,
we are
yeah, yeah.
done. We
Right,
can
right,
say
right.
that
We can
union is
prove.
also possible, right? If
True, true.
this is true, fine. Now
Yeah, yeah.
can now the question is okay, fine. Now this means this property means what it essentially means is let's talk about S1 union S2 here. Now you can't define a common normal for this union, right?
Yes.
Okay, whatever may be the reason, but at least one thing I can say. Let's ignore ki hame common we will get a common normal or not. But one thing we can say, if V plus W belongs to S1 union S2, this means this implies essentially V plus W belongs to S1 and V plus W belongs to S2. Is this true?
Or should be there, no?
Huh? Okay,
Or
yeah,
should be
sorry.
there in the middle.
Union or yeah, or.
Yeah,
Okay.
yeah, right,
Or V plus W belongs to S2, right? Is this true?
right, right. Yeah.
Right. This means V plus W dot N1 cap equals to 0 or V plus W dot N2 cap equals to 0 or, right?
Yes, yes, right. But none of them would be zero. Okay.
Now
Wow.
we
Wow. Nice proof.
what I'm saying is V dot N1 is 0 and W dot N2 is 0. And when V and W are non-zero, if V and W are non-zero vectors, you will never find such set as these.
Right, right, right.
You will never see that this OR condition will be true.
Exactly,
Fine, is this
exactly.
clear?
Correct, correct. Yeah, yeah, yeah. Very nice proof. Okay, thank you.
Yeah. So this
Yeah.
was how you prove this, and that's why zero is also known as the trivial subset, as trivial vector subspace, because zero contains all the subspaces, and zero itself is a subspace, the origin. Fine. So let's move. Fine. So let's move to, so I hope now it is clear, right? Now, why intersection has always subspace? Again, in the previous proof, what you have to check is and instead of or, you have to put in and there. Can you get from that proof and prove that option 2 is all correct? Whatever I am writing here is true. Anyone, do you have any
Yes.
doubts on
No,
proceeding
no,
from
no
that
doubts.
idea?
Yeah.
Fine. Similarly, W1 complement is never a subspace. Fine. So let's move on to yeah. Anyone, do you have any?
Excuse me. Yeah, yeah. Excuse me, sir. Like in the same one, assignment 8, there was question number 11.
Okay.
That is question was which one is not the subspace.
Okay.
So what I have opted, that is x plus y plus z equal to 5, something like that is there. So which the plane which is not passing through the origin cannot be the subspace because it is not containing the origin.
Hmm.
So yeah, I think that has been marked as wrong answer
Origin
because
should mean.
if it is a subspace means ki the plane should pass from the origin, no? And the origin should be contained means 0 0 vector must be there, zero vector should be there in that.
Answer is wrong because it says XYZ belongs to R3, X comma Y comma Z should be positive. Then where is that negative term you are getting? How can you go to zero?
No, no, I'm question is which one is not a subspace.
Ah, the
So
option
x
D is
Two
not a
options are correct
subspace, right?
actually. So actually, two
Op
options are correct. So
Option B is also true.
no, so
Yeah,
they have marked wrong. They have marked wrong, I think.
email
Because
them.
what I've considered like no x y z greater than equal to 0, so 0 is included in that. So it is not written that. So D option, I think, is also correct because it is not
Why?
correct because it is a subspace. Sir. X y z greater than equal to 0 may be subspace because origin is contained in this because 0 is there. No,
no, but if you multiply it with a negative element, as sir said, it will take you to a negative vector, which is not present. So it will lack the closure property of scalar
Hmm.
multiplication.
no, no. How come like x y z greater than equal to
Let's
0?
take this example.
Okay,
Let's take
no,
this.
no, yes, yes, that is also understood because negative will not come. This I've understood. But that option is also correct. Na? X plus y plus z equal to 5 something is there. That is also not a subspace, no?
Yeah, yeah, both options are correct. Right, right.
So
So
they
they
have
will
marked
change the
wrong.
answer. I think.
I don't
They
know.
will change it. So I have mailed them. So they will change
Okay,
the
okay.
reevaluate it.
Okay, okay. Thank you, Rohan.
Yeah.
Fine. So let's proceed with the next topic, right? Linear independence. So till now, I hope you all are familiar with the linear independence term. I've been using this a lot while deciding how many solutions will be there for a system of linear equations. Fine. So let's choose a set of vectors u1, u2 up to un. Then a linear combination is a set of real scalars alpha 1 up to alpha n such that linear combination is essentially equals to sum of paired multiplication of alpha I into ui, right? Everyone, is this clear? Do you have any doubts in this thing? In the definition of linear combination? Fine. Then what is the definition of linear independence? Again, you have a linear combination. Now they are linearly independent if and only if you can find you cannot find any set of these alpha any set of these scalar coefficients such that the coefficient is non-zero but the total sum is zero. That is not possible. Is this clear? Is linear independence clear? It is essentially saying that, let's say you have a vectors 1 comma 0, 1 comma 1, 0 comma 1, right? First linear combination. So let's assume three vector scalars alpha 1, alpha 2, alpha 3. First thing, what is a linear combination? Linear combination is anything that looks like this: plus alpha 2, 1 comma 1, plus alpha 3, 0 comma 1. Alpha 2, alpha 3 are scalars. Fine. Now the second thing is, are they linearly independent? Can you find any non-zero values of any one of the alpha 1 comma alpha 2 comma alpha 3, such that alpha 1 plus alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 equals to 0? Can you find it? I can find it. Matlab, I can see this. Choose alpha 1 equals to -1, alpha 3 equals to -1, and alpha 2 equals to 1. You will get -1 0 plus 1 1 minus 0 1. You will get 0 vector. All the three alphas are non-zero. So these are linearly dependent. If it was not the case, then they would have been linearly independent. Now they are linearly dependent. For this condition to hold, for their sum to be equals to 0, for the linear combination to equals to 0, this should only happen if the scalars themselves are all 0. If that is true, then only they are linearly independent, otherwise not. Fine, everyone. Do you have any doubts in the definition of linear dependence and independence, as well as linear combinations?
Sir, in the definition of linear independence, only one-sided implication should be there, no? Because the other-sided implication is very trivially true, and we don't need to satisfy it. So
Yeah,
summation of alpha and ui equal to 0
Yeah.
implies that
Right.
alpha equal to 0.
Yeah, that is true. Yeah, that's fine. Yeah. If you have a linearly independent set of vectors u1 up to un, and then their linear combination is this, then the set of alpha is unique form of vector. Right. If you use if the set of vectors are unique, then you will get a unique set of one-to-one mapping between the pair of alpha i's and a vector that you are getting as the linear combination. Is this clear? I mean, this is something we have done only for 2 by 2 and 3 by 3 matrices, basically two-dimensional and three-dimensional vectors. But can you relate it to the system of equations, the number of solutions to a system of equations? Can anyone relate it?
Yes, sir, sure. So
Fine, everyone. Is this clear? Fine.
So, sir,
So
it
let's.
basically says that in how you are relating it to system of linear equation. So you have basically that n basis in Rn, and that's why you are saying one particular vector can have one unique coordinate, right? Or you're looking at it some
Yeah.
way.
That's true. We are going to that only, that point only.
Okay, okay.
So basically, the thing is, if you have linearly independent vectors like this, the problem is saying, the statement is saying, if you scale them and add them up, you then if you retain the scaling factors, then you will always get a single same output every time, which is true, because if you are adding two vectors which are not on the same line, you will get the unique vector, right? Fine. But let's say if you have one vector like this and another vector going in the opposite direction like this, then you can have multiple values of alpha 1 and alpha 2 that gives you 0. Even that can give you, I mean, same values, or multiple alpha 1 and alpha 2 that will give you same value, let's say 1 comma 0, something like that. Do you agree? Is this clear? I mean, I'm just giving more intuition on this.
Yes, sir. Yeah, got you.
Anyone, if you have any doubts, tell me, right? Then again, this brings us back to the system of linear equations. If you want to check if a set of vectors are linearly independent or not, solve the system of homogeneous system of equation. If only the origin exists as the solution, or if only the trivial solution exists, then they are linearly independent, right? Simple. Just put all the vectors in a matrix A. So you put V1 as first column, V2 as second column, V3 as second column. Try to solve for Ax equals to 0. If you get the answer as x equals to 0, 0, 0 only, no other solution, then they are linearly independent. Now this property 4, like this property, this idea of checking how to check essentially comes from property 2 itself, from the definition of linear independence. It says their scaled sum will be 0 if and only if the scalars that we are multiplying them with are 0. This is essentially you put the alpha i's into the vector x, so alpha 1, alpha 2, alpha 3, and in the matrix A you put all the vectors v1, v2, v3, right? Then if you take the product and you set to 0, then the only solution is alpha 1 equals to 0, alpha 2 equals to 0, alpha 3 equals to 0. Is this clear, everyone?
Yes, sir.
Fine. Let's move on to the next thing. Span S is a definition. It essentially defines is a non-empty subset of a vector space V. Span is the set of all possible combination of vectors in S. Fine. So span is essentially set of all possible linear combinations of vectors in S. Right. So what is the linear combination? We already remember this, right? So basically L summation alpha I into summation alpha I V I. This is a linear combination, right? Now, if you define a set of vectors V1 and V2, then what is their span? Their span is summation alpha 1 V1, alpha I V I equals to 1 to 2, right? This is the span of vectors V1 and V2. So essentially all the vectors that can be reached using the two operation defines for a vector subspace, which are multiplication and scalar addition. If you use these two vector addition and scalar multiplication. If you use these two properties over a vector subspace for a given set of vectors, then whatever vectors you can achieve, whatever vectors you can reach from using these two operations on the pair of vectors, that will form a span of those vectors, right? This will form a span over vectors v i's, right? I can be arbitrarily large, right? So this is the definition of span. Is this clear? Again, for example, if you have a vector like this, then all the vectors lying along this line will be in its span. If you have two vectors, one like this and otherwise like this, then all the vectors in this plane, all the vectors in this plane will be in the span of these two vectors. Is this clear,
Yes, sir.
Uh,
everyone? If you have any doubts, you can just ask me, interrupt me and ask me.
so, uh, uh, span concept still a little bit doubt is there. It means ki
Mhm.
like if you have first of all span means it must be a subspace, because if it is a
It must be a vector space, vector space.
uh, because it is a subset, no, it is a subset, so it will be subspace.
Right. The thing is, it is a subset of any vector space.
So it means ki it must be subspace.
Ah, it is a subspace. Yeah.
Now it means ki within the subspace of that,
Hmm.
the linear combination with the scalar one, we
Hmm.
are going to reach with the other vector in the subspace, any other
Right.
vector,
Yeah.
then it will be span,
Yeah.
otherwise not, because whatever the vectors are there in the vector space, so with this linear combination of this vectors, we are going to reach any vector outside of this subspace.
How can you reach?
That only the span is there, no? I think because any it means ki, by the linear combination of this subsets, we are able to reach any vector in the vector space, not in the span itself.
No, no, no. You are getting confused. Let's think like
Nature of
this.
this actually. So,
Let's assume a general space, or uh, let's assume some space of, let's say, dimensionality m cross n. How should I say it? Or let's consider the three-dimensional space, right? Let's consider the three-dimensional space, right? Now, is this a vectored space? Are the vectors defined in three-dimensional space? Do they form a vector space?
Uh, Vector space, it must be vector space because it contains origin also. So it is a vector space.
Right? So all the vectors, so this vector, whatever vector you define, is forming a vector space, right? Now you take in this vector space, you choose two vectors, right? Let's say I'm choosing for my convenience the x-axis and the y-axis. So I'm choosing two vectors, 1, 0 and 0, 1. Fine. Now the definition of span S is it has to be non-empty, first of all. And then second is subset of a vector space. So you had three-dimensional subspace, right? Now I am taking is taking the subset of that three-dimensional space found by two vectors 0, 1 and 1, 0. Then what is the span of these two vectors?
It will be plane. I think XY plane. It will be no.
Yeah, alpha 1 into 1, 0 plus alpha 2 into 0, 1, right? And what all vectors lie in this space? This space essentially
Alpha.
comprises of all vectors in 2D space, right? Or XY plane,
Yes, sir.
right? Plane. Now, this is essentially a span of these two vectors. This is the definition of span of these two vectors. So if you take a scalar
Yeah.
if you scale the vectors and then add them up, whatever vector you can achieve, whatever vector you can reach, lies in some space, vector space, and that vector space is essentially known as the span of these two vectors. That's it.
Uh, Actually, I have misunderstood that we may reach any vector. So here, because R3 is a vector space, so in the we can't go in the three dimension because we have chosen a subspace space. So
Mm.
it will be within the region itself. So within
Yeah.
the region of the subspace, whatever the vectors we are able to achieve, that is called as a
Mm.
span.
Mm.
Okay. Thank you, sir. Thank you.
Sir, I have one small doubt. So
Mm.
by R3 3 cross 3, are you meaning the metric space or what do you mean by R3 cross 3?
Vector space of three-dimensional vectors, basically.
Okay, okay. So it is R3
Three-dimensional
only, no?
vectors.
R3 we are referring only.
Yeah, we are talking about R3, right? So it's not R3 plus 3. You're right. It's R3.
Sir, just a small doubt with a previous assertion that you have written in linear independence part that
Yeah.
if AX equal to 0 system, it has,
Uh,
where is it?
Mhm.
Yeah, right. So if only trivial solution exists, then it is independent. Then we what do you mean by independent? Then the columns are independent. Is it what you are
Column,
trying to say?
yeah. It is dependent on the definition of the matrix A, right? And the vector X. So now, what does this
Right.
matrix A represent? If you put in the columns like this, let's say we had three vectors v1, v2, and v3, and
Right.
I had scalars alpha 1, alpha 2, alpha 3, and I want to check if these three vectors are linearly independent or not. What you do? You say alpha 1 plus alpha 1 EV1 plus alpha 2 V2 plus alpha 3 V3, and you say this sum is equals to 0 if and only if alpha 1 is equals to alpha 2 equals to alpha 3, which is equals to 0, right?
Another condition should also be there, otherwise it will be wrong. So A should be square because I was trying to come up with a counter example to check this. So I
Yeah,
made the
right,
matrix
right. This
3
is
by 5.
for a square matrix, right? You are right. Because null space, it can go into null space and then
Yeah, yeah, right. So rank will have that problem. So A 3 by 5 won't satisfy this criteria. A 3 by 5 matrix.
it can belong to the null space. So this is only for the like square matrices. You are right.
Okay, sir,
But
you are
I
now
think
clear.
square matrices was not covered till Now, sorry, rectangular matrices were not covered. That's why I think this point was there. I don't know,
Oh,
but yeah,
okay, okay,
it
okay, okay,
has to
sure,
be
sir.
square. Square. Yes. Fine. So, any other doubts?
No, sir.
Fine. So the next topic
Uh,
is next thing.
uh,
Yeah.
uh, uh, like just now what Rohan has asked, no? Ax equal to 0. So
Hmm.
I was watching the video just now for the I think week 9.
Hmm.
In that it has been explained like 4 type of dimensions. No,
Hmm. Yeah. Hello.
uh,
Hello.
uh, hello. Sir.
Yeah.
Actually, there they are taking as like null space and column space. So there it is. They are considering this one part. I think ax equal to 0. So for a null space and as well as column space, they are forming. I think for a transpose x and then one for ax. So they are forming as a two part. I think, and vice versa. Something like that
Yeah.
they are doing.
Yeah.
So it is
That's
not
fine. But
necessary
that.
that it will. Okay.
Yeah. What? It's not necessary.
I'm saying it is not necessary that it will be square matrix only, because when it comes for this one case, null space and this one like column space.
Satinder,
Let's
see, the
check.
thing is ki if it is
Okay.
like if you say that this argument is true for a rectangular matrix, then I can give you a counter example that a rectangular
No,
matrix for which this happens, but that doesn't happen.
no. I'm saying you may be right, but what has been explained in the video 9, no? So in that, what I'm finding ki it is not necessary that it is a square matrix. I think they have defined 4 types of column matrix. Still, I
Yeah,
have to watch it
these are
again.
fine.
So,
No,
so that
this
you
is
may be
fine.
right.
Row space, column space, that thing is fine. So my point is that if we take a
For
matrix
the
which is of size
yeah,
3
I've
by 5,
understood. Your point is for the linear independent, it must be square matrix for this case here. If you're saying for
yeah,
that
right.
part, I think.
Yes,
Yeah.
yes. For rectangular matrix, we have to add other like
Uh, uh,
criterias
uh,
to say that the
yeah.
columns are
You're right. You're right. Okay.
right. Right, yeah.
Fine. So let's proceed. Right. So yeah, this was all about span. Fine. Then the next thing is what is the basis. Now, if you know the span, then the vectors used for forming that span can be a basis, right? If we for let's say we have a vector space V, we can and we define a set of vectors B1 up to Bk as B as a subset of V if they are linearly independent, and span of V, and they form the span of V. Their span is essentially the V. Then B is a basis of B is a basis for V. Is this clear? So very simple definition. You have a set of vectors B1 up to Bk. They have to be linearly independent. And if you check that, you go ahead and check that if their span is equal to the entire space V, then they form the basis for that vector space. Is that correct, everyone? Is this clear? Do you have any doubts in this?
Yes, sir. It is clear. I have just one doubt from this part. So zero vector space, I read that
Mhm.
its basis is the empty set of vectors. Later,
Yeah.
if you get free time, then can you intuitively tell me, or is it just a rigid definition that we have to accept so that other things uh, are valid, or like it will happen? Like this particular edge case, like it disturbs me a lot. How can a set of no vectors is a basis for a zero vector space, which is actually a contains a vector, zero vector?
Zero itself. Okay, let me think. The origin is something that is always first defined. Everything starts from something, and you have to define the origin. Without defining the origin, you cannot get anywhere else. So zero is
Right,
the
right.
trivial subspace, and it is like well known that you have to start from zero.
Yeah, zero is a trivial subspace, but the point is that what is the basis of it? Then they're saying that the basis is empty vector space, the null set. So null set is the basis for zero vector space. Now this argument, intuitively it seems very difficult for me. Like,
Let's think. Null set of what, right? So null set of what? Basis is something. Basis is a set of vectors that form whose span form the entire subspace. Now, if you take any vector set of vectors, any finite set of vectors, you can always get the trivial coefficients which are zeros that will give you zero, right?
yeah, but they will give some other vectors too. So if I'm trying to generate only zero vector space, then what should be the basis? We can't take zero because zero is linearly dependent. So zero cannot be itself the basis for zero vector space. So they take the convention that
Excuse me, sir. Like I have also one doubt.
Yeah.
Rohan, can I speak in little bit?
yeah, sure.
Excuse
Yeah, go
me.
on.
What I'm thinking, like, first of all, let's go with the span part. Span, once we have understood that the span is a subset of the vector space. So within the span, we can take any number of the vectors to take it as a coordinate system. I think it depends upon us that up to how much dimension we want to make. Like if our V is of n dimension, so span we can take like in the span we can take k dimensions also, means less than that also. It depends upon that how many vectors we can take in the span, and then that vector will form the basis for the means that will be the new coordinate system. What I'm thinking as a basis will be the new coordinate system with respect to the original coordinate system, what orthonormal coordinate system in the V space. Sir, am I right,
No,
sir?
what are you saying? I don't get your point.
No,
But let me
what
first
I,
clarify to Rohan and then we will come back,
okay,
right?
okay, okay.
So Satinder, what you're saying, just be quick, try to explain.
No, what I'm saying is basis is nothing else but is it is a part of the span. Like any one of the vector we'll consider that will form a basis. So for
If
the
they are
zero
linearly
vector,
independent.
yeah. So for the zero vector, what I'm finding there is no span for that for the zero vector. So since the span we are not getting any span for the zero vector, that's why basis is, will be empty set. That I was saying actually.
Yeah, that's fine. Huh, that's fine. Huh, that's fine. I mean, the origin, just assume that origin is defined. You have to start from some point, and that is the origin, and that's it. Like, yeah, defining the span of origin does not have any that. The only importance of origin is you should have some starting point, and that all the properties are based on the origin itself. So we don't care give too much interest to what the span of origin is essentially. What is the basis for
Span
origin?
of origin is a very valid thing. Span of origin will be origin. There's no doubt with it
Hmm.
because if you multiply
I mean
real
basis
number,
for
so
origin. Basis for
yeah,
origin.
right.
Right.
So okay, it might be that like in factorial, we have the definitions for factorial, but 0 factorial is
Hmm.
equal to 1. It is taken, right? So
No,
that
no,
it
no, no, no.
satisfies the other
There's a reason
definitions.
for that factorial thing. So let's say if you have zero objects,
Right?
then in how many ways can you arrange zero objects?
We can't arrange them, right?
Yeah, there is one way only, right? There is nothing, you
How come
keep it
one way?
nothing,
Like we cannot.
right?
Okay, but we cannot do it. It should be zero ways, no? If we cannot arrange something,
I mean, like this is not because we assume. Why is like basically if you have nothing, how can you arrange it? Like how many ways you can arrange it? It's not can you arrange it or not.
so what if someone says we can arrange it in zero ways?
Hmm?
What if someone says we can arrange it
Hmm.
in zero ways?
I mean,
No,
basically the empty arrangement, right?
wait,
Basically,
excuse me, sir.
it's yeah,
Can I clarify this, Rohan, this part? I think I
yeah.
can make it clear.
Hmm.
Like suppose we have five apples. The question is in how many ways you can choose five apples. So we have actually six ways to choose. One way, like we can choose one, either two, three, four, five, and one way is we have not chosen any. of the apple. So sir has asked that in how many ways it can be arranged. So if there is nothing, there is only one way, that there is nothing, we can't arrange. So that is one of the way. So that's why I think 0 factorial is one.
Okay.
What sir was saying, I think so.
Okay,
It's the
nice. So
empty
you were
set,
saying that
right?
not choosing any apple is also choosing it in one way, or maybe
Yeah,
It's the
yeah,
not
empty
that is
arranging
set, right?
case.
it
That's
is
why
also.
Yeah.
empty
Okay.
sets exist. And a similar thing goes on for basis of the origin. That's the empty set, essentially. Yeah.
Okay.
Empty
So
set is also
here,
a set, right? Phi is also a set.
right. So here, suppose phi is written as two, like another interpretation for phi is this, no? That curly braces in between there is nothing. So
Yeah, either this or phi.
right.
Yeah.
Yeah. So suppose we
So this
have
is also a
let's look
set.
at the yeah. So let's look
Hmm.
at the first one, that two curly braces, and in between we have nothing. And now
Hmm.
we are saying that what will be the span of this? So we are coming with real numbers. We are multiplying real numbers with this. Then how can we get 0, which is a vector, when we are multiplying real numbers with nothing? How can it will yield something?
Yeah, right. But I mean, I'm not sure. How maybe this is something which is defined. I don't know. Where did you read it?
Okay. So there is a book Hoffman Cones. So it says that
Okay.
this particular set will be basis for that, and they
Is
have
there
given
any
the
explanation?
reasoning. Yeah, but the explanation is more on that it is a convention definition, or that's why, like, because it has to satisfy the other criteria, that's why it is happening. But yeah, so still
Okay.
there was some kind of a, like, a gap I was feeling. That's why I asked. Okay, sir. For the time being, we can take it.
Hmm.
Later, I can send
Hmm.
it that portion, so you can
Yeah,
read it and
right.
yeah.
Fine. So basis is clear. Then orthonormal set of vectors, right? So basically, if two vectors are perpendicular to each other, then they are perpendicular orthogonal. And if the norm is also one, then they are orthonormal. And orthonormal set of vectors form a basis always, because we all know orthonormal vectors cannot be linearly dependent, right? And number of basis vectors form the dimensionality of this is something uh, not that relevant, but yeah, number of basis vectors for any subspace is essentially the dimensionality of subspace. For example, for 2D subspace you need to at least two bases. One is, let's say, 1 0, the other one is 0 1, or sorry, 0 1, or you can take 1 1 and 1 0. Anyway, if you want to span a two-dimensional space, you need two vectors. So that is essentially two-dimensional space. That's why we call it two-dimensional subspace. If you want to span three-dimensional subspace, you can choose three vectors: 1 2 3, 1 1 1, and 1 0 0. So these are essentially three-dimensional. These are three bases for the three-dimensional space. So number of vectors required for defining a basis for a space, subspace, is essentially the dimensionality of the subspace. Is this clear?
Yes, sir. Sir, actually, this was something which was mentioned there to support the statement that empty set of vectors is a basis for, because empty set will have no vectors in it, so the dimensionality
Hmm.
is 0, and that's
Yeah.
why we can say that zero vector space. So it was one of the support things, that if we take empty set of vectors as a basis for that, then it will satisfy this kind of things.
Um, zero. I mean, zero is what is a point? Point is a dimensionless quantity, right? And zero is a point
Right.
essentially. And zero is dimensionless quantity. So how can you define the set that spans a dimensionless quantity? That's essentially an empty set of vectors. You don't get any vector that can span, that can only span zero. If you
Yeah,
define
right.
a vector, right, if you define at least one dimensional space, then zero is not, it does not only include zero, it can include other vectors also. So what is the
Exactly.
only vector that spans the origin, the dimensionless quantity? That is essentially the zero,
Right,
but
right.
is zero is not a vector, right? Or is
Zero is a vector, like we have to take the
zero is a
definition of.
vector having a zero from the origin, of
Right.
length zero from the origin. Fine. Yeah.
Right. Let's say.
Right. So this was all that was covered in lesson lecture 8, right? So let's go to lecture 9 very quickly, and then we'll solve the problems. So in the week 9, what you were taught about is what is null space, what is range, what are row and column space, nullity, rank nullity theorem, then orthogonal complement subspaces, which we have already seen in some form, and then orientation of fundamental subspaces, right? So these are the topics that were covered. So let me go through them very quickly. Null space, everyone, are you familiar with null space now? So now we are talking about general rectangular matrices. Let's say a matrix that looks like this, 0, 1, 1, 0. This is again, it's not a rectangular matrix, it's a square matrix, but again, you can see a null space in this matrix. What is the null space of this matrix? Anyone?
1 1 minus 1.
Okay, this is linear independent. No, this is right. Let me change this to a more simple example. What is the null space of this matrix?
0 0 x, where x can be any real number.
0, 0, x, right? So anything in this that direction is belongs to the null space of this matrix, right? So the definition of a null space of a matrix is set of all non-zero vectors, basically. Yeah. Such that AB equals to 0. Sorry, all vectors, non-zero. No. This has to be all vectors because 0, if you want to define a vector space, you have to include the origin. So set of all vectors V belongs to Rn such that AB equals to 0. This is the definition of null space of matrix A. Fine, everyone. So let's say you have a rectangle matrix like 1, 2. Uh, let me make it like this: 1, 0. Sorry, 1, 0, 1, 0, 0. Let's say you define this rectangular matrix, right? So then the null space is 0, 0, x, right? Where x can be anything in the real number line. So it can be 0, it can be 100, it can be minus 100, whatever you want to choose, right? So is this clear? The definition of null space, everyone?
Sir, why you dropped the third column? Didn't get that part.
I would just want to give an example on a rectangular matrix also. Like you don't always have to deal with the square matrices. You can always have rectangular matrices and define then these properties over.
Okay, but here null space will only be 0 and 0, no? It is coming. It should be coming from a R2 space.
No, this is a 3-dimension, 3 by 2 matrix, right?
It is okay. Yes. So the null space
I'm
should
just
be 2
talking
by
about
1.
null space of matrix A. I'm not talking about the 3-dimensional or 2-dimensional space.
Right.
I'm
So
talking,
if A is 3 by 2 matrix, then
yeah.
its null space should be 2 by 1 matrix. Wrong?
No, null space is a vector space, right? It's a 1-dimensional space. So we will see what will be the dimensionality of the null space. But just going from the definition, can you feel what null space means? First of all, it has to be a vector space, right?
Right.
So now we are not talking about matrix. Null space is not something matrix like. It's not matrix, right? It's a vector space,
Right. But the
right?
point is that if the matrix is 3 by 2, then how come the
Hmm.
null space contains a vector of size 3 coordinates? It should have all the vectors in it which have the sizes 2, because you
Why?
need to have AB equal to 0. Because AB should be 0, na? Matrix multiplication won't be possible then. A is 3 by 2. How
Oh,
come
right,
B
right,
be
right, right.
right?
You're right. So, acha, this is a full rank matrix. Yeah, you are right. Um, okay, not a problem. Let me make this 0. Fine.
Right, yeah.
Now,
Now
what is the null space of this vector?
1
1
minus
minus
1.
1. Any vector along this line, right?
Right. Yeah.
So that was previous example was also perfectly fine. Just for that, the null space was origin. But for this example, you have origin plus this vector direction. Fine. So this is the definition of a null space. Then what is the range? Range is essentially,
Uh, Excuse me, sir. Like, can you
yeah,
again explain that one? I'm not getting like how it is that part. Like, if I'm writing AV equal to 0, so
yeah.
how come we come out to be like it is null space that little bit.
Null space is a definition. So let's say if you have a vector V, sorry, if you have a matrix A, then we have some quantity defined for the vector matrix A. One is null space. So what is this null space thing? What is the definition of this null space? You define some quantity. Now you need to define, give the proper technical properties of what it should satisfy. So the property that it should satisfy is all the vectors, let's say all the vectors that belongs to null space of A should satisfy the property that AV equals to 0. Now, this is one property that we are looking out for. If this is true, if for a given vector V, AV equals to 0, then V belongs to null space of A. Now, what is the trivial
Like
null space? Origin, right? Origin is a trivial null space that
0,
always exists.
0.
Hello?
Yes.
Yeah, is
Yes,
this
sir.
clear?
Yes.
Do you have any doubts
But
in this?
my concern is like A we are taking 3 cross 2. No, 0 0 to this I'm understanding this part. Like it is a trivial solution that part. We are solving in a homogeneous way, I think.
Yeah, but now let's
Like
think of this 3 cross
if A,
2 example also.
mm,
Now I'm saying what are all set of vectors. So basically 3 cross 2. So all the vectors that can do matrix multiplication with this matrix is two-dimensional vectors, right? Vectors belonging to R2. So what is the vector V such that V belongs to R2 and VAV equals to 0? You will see that that will be a vector along this direction. So any vector V is equals to K into 1 minus 1. That's what I'm saying. Is this clear?
this part also I'm
Hello? Your voice is breaking. So let's think of matrix
in
product
the same span,
as,
linear span.
so let's think of
Okay,
this like this. In the
I've got
first
it. I think.
lecture, in the first lecture, first or second tutorial, I explained that how do you think of this matrix vector product, right? Think of it as a function mapping from input domain. Let's say we have some domain and you have some range. This, right? You have, whenever you define a mapping, you define these quantities, these sets, right? And A, a is a function that takes inputs from the domain and puts it onto onputs into the range. Are you familiar with this view of a mapping? So A is a map, right? A is a map between two sets. Set one is the domain, set two is the range. Is this, I hope this is clear to this, everyone is familiar with this idea, right? Now, when I talk about
Yes,
a
sir.
matrix of dimension m cross n and talk about matrix product over a vector space, again you define a domain and you define a range, right? And now let's restrict these two sets to vector spaces. Now what are these? These are vector spaces. So set of vectors in this vector spaces. Then what is the first thing you want to check? That 0 exists in both these sets, right? Because they have to be a vector space and other properties of vector spaces. So 0, and then there are some other points in this space, right? So consider each point as a vector in both these spaces, in the both of these sets, right? Now you define a mapping between these two, A m cross n. What it is doing? All the vectors in the domain belongs to the Rm space, the Rn space, and all the vectors in the range are belonging to the Rm space. Now you have to pay attention to this thing. Is this clear? Rn and Rm
Yes, sir.
spaces. Fine.
Yes, yes,
So
yes.
this is how you should look to onto matrix vector product. Don't think of it like dimensionality and whatever stuff. Just think that matrix vector product is essentially on of mapping from a vector to another vector. That's it. And how are you are doing that mapping? You are doing using some rules defined as what is the value of ax, right? That's it. Now let's take this picture and define some properties. So now this is the domain space of matrix A, right? It contains all the vectors in the space Rn, and this is the range of matrix A. That's why you call it range space. Ax belongs to Ra. So this you will see, right? Now let's define some properties based on this picture. First one is null space, right? So now you can see in the range space, the set range essentially contains the zero vector. Why? Because the range space set is a vector space. If it's a vector space, it has to contain zero. This means, and again, for a function, you know that you have some input, and when you pass it to some function f, you get some output, right? For matrices, this means a into input is equals to output, where input is a vector and output is again a vector, right? Now I'm saying a into some vector v equals to zero vector in the range, right? Are there any vectors? If there are such vectors in the domain, right? If there are some such vectors in the domain, they will form, you take all those vectors, take all those vectors v in the domain, right? Such that AV equals to 0 and find their span. Second step, find their span. This will find that will find form a vector space again. This will again be a vector space, and that vector space is essentially known as the null space of A. Now, is this clear,
Yes, sir. Got it.
everyone?
Yes, sir. Yeah, understood.
Now, the second definition is range of A. I don't need to explain anything here. This is the range space. Is this clear?
Yes, sir. Yeah.
Now, one would think that any and m-dimensional space, all the vectors in the m-dimensional space belong to the range space of A, but that is not true, right? Like whatever information I have given right now, just from this picture, one would believe that all the vectors in the Rn space belong to range of A. But what I'm saying is that's not true. So let's proceed. Let's consider this the Venn diagram, and this universal set essentially contains all the vectors in the space Rm. And what my claim is, there is a set that is basically R of A. That's it. There is no infinite. And then there is a set N of A. Everyone, do you agree with this? These are disjoint sets.
Sir, NA should be not in this part, right? NA is coming from Rn. So
Acha,
N of
oh,
A
right, right.
transpose should be yeah.
Yeah, yeah, N of A transpose. Yeah, we will see that. Let's ignore that here. Yeah, you're right. Okay, fine. So, do you agree with this? I'm saying RA is not is involved. Not so basically R. So when I want what I want to say is RA complement. And if you take the cardinality of this, if you take the cardinality of this is not zero. That's what I'm saying. It may or may not be zero.
Yes, sir.
Everyone, do you agree with this?
Right, sir. Yeah.
So that's why we define the range also, the range space of A, right? So you take all the possible vectors from the input space from the domain and get the possible output vectors. take their span, and you will see that that will form a subset of the space Rm, right? And I'm not saying proper subset, I'm just saying subset. So it can either be Rm or anything Rk, or anything Rk where k is less than m. Oh, sorry, less than m. K is less than equals to 1. Fine. So that will form the range space of A. Why we will get some k less than m? Again, this null thing, this um hmm, yeah, will it okay, if it's a rank deficient, yeah, this null space thing will help you out how to think of this. So let's say I'm taking a vector like this, 1 0 0 0 1 0 and then 1 1 0. Fine, let's take this vector, and then you define the this is a 3 cross 3 matrix, right? So 3 cross 3 function. Now you define the input space. The input space is R3, right? So you take some input x, y, z, and you get so let me take not x, y, z, v1, v2, v3, and you get the output x range space x, y, and z, right? Now one would think that x, y, z belongs to entire R3. But my question is this true? Anyone? This is true. This is true. XYZ belongs to R3. Is R3 equivalent to XYZ, or basically R3 is equals to XYZ? The question is this. Anyone?
No, actually,
No, no.
because no set component can be generated. So set component, no one can generate there.
Right. So basically, whenever you do this matrix vector product, you will see that you will always get XY0. So there are vectors 0, 0, k that belong to R3, and they do not belong to range of A, right? So that's why I'm saying there will be some non-zero vectors here. And that's what I'm saying. That's it. So basically, set with non-zero cardinality outside the range of A. So it's not that it spans entire Rm space, it spans some subset that can be or equal to M or less than equals to M, right? Fine. So this was the range space of a matrix. Then we saw the null space and the range, right? Then the third thing is row space and column space. Now, since we were,
Uh, uh,
yeah,
Excuse me, sir. Can like we have taken a square matrix, no, 3 cross 3. Can we take like 4 cross 3 with that? What you have explained, 4 cross
yeah,
three
right.
matrix. Can we take that?
Yeah, we can take always. We can always take 4 cross 3 matrices, right? So that's what I was going to explain now. So till now we were talking about only square matrices, whatever, in some form. Let's think of rectangular matrices also. Let's start with the square and then proceed to the rectangular matrix, right? Now we had this matrix 1 0 0 0 1 0 1 1 0, right? Now this is the matrix A. Now you take three vectors 1 0 0 alpha I. Take the linear combination of these three vectors 0 1 0 plus alpha 3 1 1 0, right? Now consider these vectors beta 1 into 1 0 1 plus beta 2 into 0 1 1 plus beta 3 into 1 1 0. Can you find the can you see what I'm doing here? What are these vectors associated with betas? Anyone?
Beta 2 will be 0. With beta 2, it will be 0 1 0. No, I think
Why?
beta 2. I don't know. Maybe you have explained with that part.
Oh,
I think
sorry,
just this.
beta 3 is 0 0 0. Okay, 0 0 0 is it. Now it's clear, right? Everyone, is this clear?
Yes, sir. So what was your question? So you are asking what betas are? Or
No, my question is, can you see what I'm doing here? This is a linear combination one. So let's call this
oh,
linear
right, right, right.
combination as LC1, this linear combination as LC2. What is the difference? Basically, LC1, if you take the span of
We
all
found
these vectors,
columns and later it is rows.
yeah, span of column vectors of A, and LC2 is span of row vectors of A. Now you get to the definition again. What is the row span and column span, right? So essentially this is it. So what is the linear combination of what is the span of these three vectors and what is the linear combination of row vectors? You will get their spans. Is this clear,
Yes,
Yes.
sir.
everyone?
Sir, in that picture, when you are saying that A could be looked as a transformation from
Yeah,
Rn to Rn, right? So in
yeah.
that picture, can we identify what A transpose will do? Surely it will be a transformation from Rm to Rm, so the side will change. But
Hmm.
what will be its objectivity? Can we find or can we relate A transpose with this picture, or it is completely
No,
different?
it's different. It can be related to this if A is an orth. No, it can't. Sorry, it can't. For general matrices, it can't. But if A is a
Uh,
square matrix and orthogonal, basically orthogonal matrix,
right, right.
then
Then it is inverse
that will be
operation.
the
So it is
inverse operation,
okay. Okay.
but not for
And in
general
general,
matrices.
okay, okay.
Fine. So this is
Okay, sir.
clear. Row span and column span, right? And then nullity, dimensionality of the row space. So whenever you want to talk about the row space of a matrix, you do what you do simply, you know the definition of null space and range of the matrix, right? Everyone?
Yes, sir. Yeah.
Fine. So what you do, you consider, now let's ignore so this was basic definition of what this row span and column span looks like. Now let's take some interesting matrix where we can actually see the difference for the spaces. So let's take this matrix 1 1 0 and 1 0 0. Let's take this matrix 3 cross 2 matrix. Let's take this matrix and let's define it as A, and let's take this matrix 1 1 0 and 1 0 0, right? Yeah, and this is A transpose. Right. Now let's define two maps here side by side. Let's do everything side by side. Okay, fine. So let's take two spaces here, two mappings. Now here I'm saying this is 3 cross 2, so it takes from R2 to R3, and this takes from R3 to R2. And this is A and this is A transpose, right? Now, if you have this kind of mapping, can you find out the range space and the null space of these two mappings, everyone? This contains 0 and some other elements.
Yes, sir. Yeah.
Everyone, do I need to explain anything here?
So in similar way only we'll find how we did for A. Similarly, we do
Yeah.
it for A
So this
transpose.
is essentially, this will give you the column space and column null space, right? And this will give you row space and row null space. Fine, everyone, is this clear? You know, for a given rectangular matrix, you can find, how can you find the range and a column range, basically. Let me type a range here. This is basically the range space. So you know this, how to do this for general rectangular matrices. So you have two different matrices, A and A transpose. You can always figure out these things. Is this clear, everyone?
Sir, by column null space, Are you trying to mean only null space and that left null space? Which is null space and which is left null space here?
Okay, so null space. What is null space here? Null space is AV equals to 0 such that V belongs to R2, right?
Yeah, right.
And this null space is A transpose V equals to 0, V belongs to R3, right?
Right, right, yeah.
These two vectors are not same, right?
No, no.
Fine. So let's try to figure out V here. For this, NA is essentially 0, 0, 1 into K. Am I right?
No, it should be R2, no? R2 kind of thing. It's 3 by
Oh,
2.
sorry. Okay. Yeah,
So full rank
yeah.
matrix 0, 0 will only be.
It's a full rank matrix, right? Let's
Right,
make
right.
it non-full
0, 0 will
rank.
be.
I don't know why I'm always writing full rank.
Okay.
Okay, let's make it full rank. Now I'm happy. Now I'm happy with this. Now, what is the
Yeah.
null space of this?
0, 1. Any line passing here.
0K, right?
Right.
And then what is the transpose matrix here? The transpose is 1, 1, 0, 0, 0, 0, right? Again, what is the null space here?
Should be 1 minus 1, 1 minus 1, and any other 1 minus 1 and Z.
Right? 1 minus 1 and kz. Basically, k into यहाँ पे s, maybe let's call it s here and k multiplied by this.
Okay.
Fine?
Yeah.
Yeah. Now you can see in this case null space is one dimensional, right? In this case the null space is three dimensional, right? Sorry, null space is two dimensional
This
vector
is
here. Sorry, two dimensional vector, right?
yes.
Null space belongs to R2, right? Here. And here null space belongs to R3, right?
Right.
Right?
So
Is this
using
clear?
first two coordinates, we can
Yeah.
write t and minus t. Otherwise,
Yes,
it will be little
zero,
confusing.
zero K will be. I think it is one dimension only.
No, this is a line in two-dimensional space. That's what I'm saying. That's simply.
Okay.
I mean, whenever you look at a line and you forget all other things, at the orthogonal space, then you essentially get a one-dimensional space, right? So
Right.
yeah. So is this clear? This is a two-dimensional space, and this is a three-dimensional space, null space of A transpose, right?
Right. Yes.
So this first A, when you look at A, you are essentially looking at its column vectors. So this is column null space. And on the right hand side, you are looking at A transpose, which has the row vectors, which is essentially the columns are the row vectors of matrix A. So this is the column, a row null space of this matrix. So these are completely different spaces, right?
Yes, sir.
Uh,
Fine.
Sir,
Yeah.
is there a term like this column null space or row null space, or people generally say null space and left null space, or is there a term like can we use this column null space and row null space?
Acha, I think, okay, yeah. So this is, I'm writing column, sorry, I'm just writing column null space and row null space to give you an idea. Basically, just be like clear on the idea that how to get to this. So you essentially look
Okay.
at the column vectors, you look at the row vectors. That's it, right? The definitions
Okay, sir.
are there, but how to get to there? That's it.
Right, right.
So
Okay, sir. Yeah.
whenever you define, if you are able to define the null space and the range space for a triangular rectangular matrix, you can always define the null space and range space for its transpose versions also, right? And the one in which the columns form are essentially the column vectors, then it is the column space. It is looked at as a column space, and if it are the row vectors, then it is known as the row space, which is essentially A transpose. So these are the two basic definitions.
Okay,
uh,
sir. Yeah, got you.
sir, what you have given the example just now for null space. Uh,
Hmm.
we have taken an example this one 3 cross 2 matrix.
Hmm.
So can we calculate over there? Can you solve for that one? So column space over there. What I'm thinking, like column space and null space, do they have the common elements also?
No,
Common
I mean
vectors.
zero, 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 zero origin. No, no, they don't have.
But sir, column space, if you are saying so, it is a part of vector space, and null space is
Okay.
also a part of vector space.
I mean, intersection
You
zero
and
is always there. Origin is always there.
Or origin means ki they have the common vector must be there, no? Because both. So can we solve for the range so that I can get the idea also for the range one? Just now you have given the example of 100, 110, and I think 000
Satinder,
for that.
so, sorry to
Uh,
interrupt
uh,
you. Though they do have origin, though column space and null space they have zero vector, but these two zero vector are not same. The column vector, the zero vector in column space, it has 000, so it is coming from R3. But when we are talking about the zero vector in null space, it is coming from 00 in R2. Though we are saying zero vector interchangeably, these two zero vectors are not same because the
okay,
two spaces are different
got
in
it, got it.
R3 and R2.
We are
Right, right.
for the column if we are saying in the 3 dimension, and for this we are saying in the 2 dimension part.
Right, exactly.
Origin.
For this particular example,
Okay,
yeah,
okay. Thank you for that.
yeah,
Yeah, fine. So yeah, this is for it for like this is basically what I'm saying is if you know how to find the null space and range space, you can always find the left null space and right null space, whatever you want to define. And that is essentially taking the transpose of the matrix and looking at the null space and the range of that matrix. That's it.
yes, sir, got you.
Okay, fine. So let's move further. Okay. What is the rank nullity theorem?
Can I,
Now the next thing.
so can
So,
I just ask you
excuse me,
one
like
small thing, a little bit off
Yeah.
topic?
one.
Yeah. So this is a very good thing actually. I was also trying to do this. Like after the class, I'm trying to jotting down the points so that I have the points in a page which I can easily recall or recollect. So
Hmm.
can you give me some tips on this, like how you are exactly doing this? So or how this can help us like to memorize or recall all the points in one page. I have never done it, but I feel that if I do it, it will be helpful for me. How you have
Like what?
how you have written the entire week's points in bullets. So how can I how to do that actually?
So essentially, for my side, I know what things are actually what things are actually there. What is the basic things that essentially makes up the subject, right? Makes up the topic. So I don't go into the details because I have already done a linear algebra course, so I already know the details. I just need to go through the topics
Right,
which are
right.
being covered, and from there I can build up this pointer. So it's not it. You will get to it after you have done the course. You will get an idea how things are going on.
Can you give us some tips like how to make this kind of short notes or how you used to do? Suppose you are taking the lecture instead of me. So can you see what you would have done so that I can exactly like take something from you and do that myself as well?
I will pay attention to all the first iteration. I will write down all the topics, every topic, whichever is there. In the second iteration, I will try to find a pattern. Like for example, in this case, if you understand the definition of null space and range, you can always define the run space and range of the row space and column space. So then from in the second iteration, I will remove all the details present in these two topics. Then I get only one big topic and two smaller topics for which I have a relation. So this is how actually I do.
Right, right. So it's nice actually. Like it in a very small amount of time, I'm feeling that okay, I'm recalling everything which were done in
Mm.
all those videos. So I will do this actually. Yeah. Thank you,
Yeah.
sir. Yeah, Satinder, you
Okay.
were saying something. Please go on.
So actually, can we take one example for that to form a column space and a null space? Like just now we have given the example there, we have got the null space. So
Mhm.
that can continue to get the column space also. So the picture will be more clear.
Yeah, the column space for this. So basically, the range of A, right? Range of A
Yeah.
is the range
Yeah.
of column space, which is essentially any alpha into 100, alpha 1 into 100 plus 110, sorry, plus alpha 2 into span of these two column vectors. That's it. For here, the range of A transpose is essentially beta 1 into 1 0 plus beta 2 into 1 0 plus beta 3 into 0 0. So basically take the span of column vectors. That's it. You will get the range. And by span, what I mean the linear combination.
Uh, it means ki for the column space, what you're finding, we are getting the some other vector part. Like it will be means it is a system of linear equation to solve, not homogeneous one.
No, why we are talking about homogeneous equations here?
No,
We are not interested in homogeneous equations here.
no, for null space, so we have to consider the homogeneous equation, no, to get that
But
null
for
space.
null space, but if you're try to find the range of a matrix, right? Range space of a matrix for
So
even
it will be,
column or row, what you have to do? You
Mhm.
just have to take the span of the column vectors.
It will be in
That's
the
it.
within the span, means ki any one of the vector we will get this only, I think. Thank you, sir.
Any one of the vectors mean?
Means I am saying in the span of that, whatever the span is formed, so with the basis we may reach to the any vector, no, with the linear
Yeah, right.
combination.
Yeah,
That why.
yeah, right. Any vector, yeah. That is right. Yeah, fine. So fine. This brings us to the most interesting and most important property. Most important theorem, one of the most basic theorems in linear algebra, that is rank nullity theorem, right? Now, for this, we need to know a few things. And before, we all know the dimensionality. What do you mean by the dimensionality of a space? Of a vector space?
Number
Anyone?
of linearly independent vectors in the basis. A number of vectors in the basis actually.
We can always say number of basis vectors, right? Now, let's say, um, okay, let's be linear space change domain. Right, right. Makes sense. Now, let's say we have a matrix A that is mapping from a domain to a range, right? This is the domain, this is the range, and you have this mapping like this, right? And zero is all obviously, since we are dealing with vector spaces, zero is here. And A is M cross N. This is N, this is M, Rn, Rm. Then the rank nullity theorem says that let's call the domain as a domain space. Let's give some name to this set. Let's call this set as D, and let's call this set as so I can't use R, so let's not take these names. Let's take this input set as input, right? And let's take this output set as output, right? Then the rank nullity theorem says that rank of the matrix A plus, so nullity is basically dimensionality of, dimensionality of A, a null space of A, sorry. Null space of A is equals to dimensionality of input space. Of input space, which was IP. Right. So this is the rank nullity theorem for a matrix transformation from domain to mapping vectors in the domain to the vectors in the range, right? Now let's see what it says. It says, let's say you have a vector matrix A, you can find the null space of A, you can find the basis of that null space, right? Then take the number of these bases, you will get the dimensionality of null space, dimensionality of an A, and you add this number of basis vectors with the rank of matrix A, and you will see that this will add up to the dimensionality. Basically, you take the input space, find the basis, right? And then you find the number, take the number, you will get the dimensionality and what dimensionality of input, right? You add these two, you will get the dimensionality of the input. So this is the rank nullity theorem, right? Fine. So let's see what it means. So again, let's take this example, simple 3 by 3 basis that we already know. So let's say this is our matrix and it maps vectors in R3 to vectors in R3, right? Now, let's forget about rank. Let's say we don't know anything about the rank till now. What is the dimensionality of null space of A? Anyone? Can you tell me? Dimensionality of null
0.
space of A? It's a
Zero,
0.
zero.
0, right? Then what is the dimensionality of input?
3.
Anyone?
Three.
3.
Three,
So
three.
the statement says the statement says rank of A plus 0 equals to 3, right? This says rank of A equals to 3. Right? Now let's take another example. 1 0 0 0 1 0 0 0 0, and let's call it, let's remove this, and 1 0 1. Let's put it here and then again do the same mapping. So now again, what is the dimensionality of null space of A?
1.
Fine. What is the dimensionality of input? Again, it does not change, so 3. So it says rank of A plus 1
Input is
equals to
2
3.
only, no?
Huh?
Dimensionality of input should be 2 in this case.
No, 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 3 equals 3.
First, no, first and third column are same. So rank deficit it is.
No, no, it does not change the dimensionality of the input, right? You
Oh,
can
okay,
always
in okay,
do
it's
this.
input. Okay, okay.
Yeah. Ah. Now this
Oh,
gives us rank of A as 2, right? Fine, everyone?
yes, sir.
Fine. So this is the definition of rank, and this essentially is defined using this rank nullity theorem. Fine.
Like, so you have taken the example just now.
Yeah.
Can we rewrite that one again in the form of 3 cross 2 so that picture will be more clear? Like, I think you are making in the form of 3 cross 3 by adding zeros only.
Yeah.
Just now you have shown. No? So can we remove the zero and then can we think of that part?
Uh, Wait. This example.
Just now what you have solved. Like last zero
So.
zero one. If I'm going to remove, and then we are going to
Mhm.
think. Like 000, if I'm going to remove that there, so it will be 10 01
Mhm.
and 10.
Okay.
So 10 is again repeating, so we have to rewrite that again in the matrix form, or should we ignore that part because it is the same thing?
Why you want to ignore this? This is a new
No.
matrix, right?
Okay.
And
So
then
that is
again, nullity is dimensionality of the null spaces. What is the dimensionality, anyone?
Um,
x1 x2, so x1 it will be
1, I think.
x1 x2 x3.
1 will it be?
One one.
It will be 1. Yeah. It will be 1. Yeah.
Fine. So if this is 1, and then what is the dimensionality of input?
It's 3.
3, right? Then what does this say? Rank of A plus 1 equals to 3. This gives us rank of A equals to 2, right? Is this true?
Yes, sir. Yeah.
Fine. So again, you can relate this to nullity thing to all these things using RREF forms, right? You remember that.
Yeah.
Now, what is the meaning of this rank? What does this rank says? This is essentially saying that number of independent columns of A. For any matrix A, rank is defined as the number of independent columns of A.
Or maybe rows of it.
No, the definition is for columns only.
Okay, okay.
You can define this for rows, then you shall have to say specifically that this is row rank. In general, it is
Okay,
just
okay.
math, so you can define any convention you want. But uh, 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 but just be very clear what is the convention that you are choosing. For example, generally people say that column rank is the rank of the matrix. So if you again start using the row rank of a matrix as the rank, then it will create ambiguity. So the best is you call it column rank or row rank, right? So for me, rank is the number of independent columns of A. So this is essentially the column rank, I will say.
Okay. I was saying because these two will always be same, no, right? So no one will have confusion whether we say row rank, column rank, or rank. So ultimately we
Yeah,
have
yeah,
the
yeah.
same number. Okay, the
Yeah,
convention
the
you are
number
saying.
will be same. The number will be same always.
Right, right.
So you don't rank is basically one to one mapping. So you get a matrix, you get one single rank. You can't have a matrix with two different ranks. But you have to be very clear in this, like what idea you are trying to use, like what view you are trying to see. You are seeing the row vectors or column vectors. That's it,
Okay, sir. Yeah, got you, sir.
right? So this is how rank is defined. And can we? Okay, let me think. Hmm. Let's say I have a n-dimensional space, and the one dimension is going there. Nice. Yeah, nice, nice. Okay, fine. So rank is clear, everyone, right? Rank nullity theorem and rank stuff, right?
Yes, sir. Yeah.
Now this brings us to the next interesting thing. Given a subspace V, W of V, subset of a V, the orthogonal complement subspace. So definition of an orthogonal complement subspace, right? Again, is the subspace found by the vectors V such that x dot V equals to 0 for all x belongs to W. So let's say you have a set V, right? Can you see this set V in this Venn diagram, right? So in this vector space, set of all the vectors in this vector space, you have two different vector spaces. One is W and one is W complement perpendicular, right? Which is orthogonal complement subspace. The definition of W perpendicular is x dot V has to be 0 for all x belongs to W, right? And V belongs to V. Is this clear? Is the definition clear? Everyone,
Yes.
right?
Yes,
Everyone,
sir.
is this clear?
Yes, sir.
Sir, what if? So I'm thinking that uh, suppose we have a straight line along
Hmm.
x-axis.
Hmm.
So we are considering the line generated by 100,
Hmm.
and and we are saying that the y-axis it is perpendicular to it. So all the
Hmm.
vectors that lie on y-axis they will be perpendicular
Hmm.
to the former one. So can I say
Hmm.
that y-axis is an orthogonal complement of x-axis in R3?
Yeah, yeah, yeah.
But I'm not taking z-axis. So is it orthogonal complement or
Hello.
will it be only a orthogonal subspace? Hello, hello, sir.
Yeah, yeah, yeah. Yeah.
Can you hear me now?
Yeah, yeah. You are audible. So
Right.
what you
So
were saying is, right, so there are some properties also that you need to satisfy, that dimensionality of U is essentially dimensional of W plus dimensionality of W complement. So since x is one dimensional x-axis, so y itself is not the orthogonal complement space. Both y and z plane will form the orthogonal complement because of this property number 3.
okay, okay. So we have to consider all the orthogonal vectors. Okay. Right, right. Yeah, got you, sir.
Complement operation, it's like set in set theory when you do the take the complement of an element
Right.
of a set, right? All the
Right.
elements that are not in the set lie in the complement set. That's it.
Yes, yes, agree.
Excuse me, sir. I have also a doubt. Like for the orthogonal complement set, I have the doubt that like if it is a W is a like one subspace, and orthogonal complement will be W perpendicular. It is written, I think so. So
Yeah,
if
yeah,
it is
yeah.
a W perpendicular is a complement, so how 0 0 will be in that also? This I'm not understanding. How origin will be contained to both? Because if it is a complement, so the set theory says ki if one is present in that, so one of the set, so that
Right.
element will be not present.
It's not exactly complement set, but it's orthogonal complement. That's why it's calling orthogonal. So that's
So
why we are giving it a special name, right?
okay,
We are not saying
okay,
it's the complement set. It's
okay.
orthogonal complement whose definition is given like this. All the vectors x dot v has to be 0. So this also includes the 0, which is will be the intersection of these two sets, which is I have modified the Venn diagram to show here.
Okay, okay. Like it doesn't means we don't have to take into account of the meaning of the complement. It is little bit
I mean,
refinement there.
yeah, it's there are more conditions to that. Yeah.
Means zero will be. I think zero will be the common point of both.
Hmm.
Zero vector.
Hmm. And their union has to be complete or the entire set. So this is not this looks like a complement operation, but not exactly that.
Okay.
Right. Now, since you can all you are considering now again the last property I want to deal and I want to discuss today, and the next things will be covered in the next session. Is do you remember when you were trying to do the projections or reflections of vectors along a plane? Anyone, do you remember this?
Yes, sir. Yeah, yeah.
If I want to find the reflection of this vector along this plane, what I would do? I will
So
just write this vector. So let's,
subtract.
yeah, yeah. So let's call this n cap A, and this is vector B. What I would do?
So we'll do v minus uh, av, I think.
Let's ignore that formula. Let's think how we get to
Oh,
that formula, right? So we can say that V is equals to, let's call this vector V proj, right? Projected V, which is basically orthogonal projection of V on the space A. Then V is equals to V proj, right? Plus, let's take this vector V n cap. So basically its complement component along the n cap direction. Do you agree with this, everyone?
yes, I can.
Fine. So we were able to write this, right? Now, why we were able to write this? Because we were spanning the entire space in which we was defined using the plane A and the vector n cap, right? Do you agree with this?
Yes, sir.
Fine. So now, if you look at that picture and just think of this property 3 and 4, can you relate it? Can we say that the space A, the orthogonal complement for the normal is this space A, or vice versa, that is the orthogonal complement for the space A is the normal vector, all the vectors in the
Yeah,
normal
yeah.
direction, right?
Right
So
side
this is
and left side.
something that we have already seen, right, in some form.
Yes, sir. Yeah.
And here there also we were trying to write it V equals to V proj plus V n cap, and that V proj is alpha into W plus beta into V perpendicular, which is beta into n cap, right?
Yes, sir. Right.
Fine.
So
So yeah, this was,
with
yeah.
two, the union. So uh, how come their union should be? So the thing is bugging me is this. So I have x-axis. I have the vector space generated along
Hmm.
x-axis 1 0 0, and the orthogonal complement to it will be yz plane, right?
Hmm.
Uh, is the orthogonal
Yeah.
complement yz plane only, or like all of the family of planes parallel to yz planes?
Okay, acha. Okay, nice. Fine. So we are always talking about vector space, subspace, right? Subspace is a itself is a vector space, right?
Yeah, right.
Subspace itself is a vector space. And each vector, the what is the first definition of vector space? It must have origin, right?
Right. Yeah.
So which
Okay.
spaces, which are the planes which are perpendicular to the x-axis and have the origin?
Okay. Nice. So it is only YZ plane.
Yeah.
So then their union won't be V, no? Then their union won't be R3.
Their union will be R3, right?
How come a
Okay,
straight line and
acha.
a plane's union?
Okay. So, yeah. Okay, from where did I take this union term? You're right. It has to be exactly the subset.
We can write a
Uh,
say something. I think direct sum or some kind of terminology should be there.
a span. It has to be a span.
Span of right, right.
It has to be a span. Let me check the notes if I took something wrong here. Okay. Orthogonal section. Acha, this has to be a span. I don't know why. So this is wrong here.
Okay, okay.
Let
So
me
we have to
remove
say the
this.
span of the union.
Hmm. No, you just have to say span of union. That also works. Yeah, you can always say. But I just want to remove this line.
Okay. Okay, sir. Yeah. Now clear.
Hmm. Fine. Yeah. So this is it, and then every vector can be written like this. We can always prove that this will be a unique vector. Fine. And the last thing is orientation of the subspaces. So we already saw the what is the null space of A, what is the rank space of A, range space of A, then again what is the null space of A transpose, range space of A transpose, and I hope you can relate this to the topics covered in the lectures. Everyone, do I need to do anything here?
No, sir. The definitions are understood. If you can solve many problems, it will be helpful.
Yeah, I will now. I
Sir,
since I've
sir,
yeah.
I'm saying only one question can we do for on the basis of this one, like a rank nullity
Okay,
one.
so I I
One
I
only one.
I, I I want to cover the problems in the next session because time's up, right?
Okay, okay.
Okay.
I think
And
if we do one question, no, so then we can get the a little bit clear picture. Only one question, short.
let me see if I have this.
And sir, before the next class, can we get the questions so that we can try ourselves as well, or we can try the next day also? Like we can try along with you on the go also we can
Hmm.
do, or
Yeah.
do you want us to try earlier them,
Hmm.
or on the go we'll do?
Okay. Okay. Fine. So let's look at this problem, right? So consider the matrix A that looks like this. Fine. We have this matrix A that looks like this. With respect to this matrix, where is this team? Yeah. With respect to this matrix, these are two statements, and we have to choose the correct answer. So let's ignore the statements. First, try to solve this. So, what is the column space of A?
Span
Anyone?
by these two, yeah, span of these two. So a constant into 1, 2, 3, 4 plus a constant into 2, 4, 5, 8.
Hmm. So, what is the dimensionality of that column space?
2.
Right? So, mm, yeah. So, column space is two-dimensional, right? Two-dimensional. And then column space. So basically, by column space, what I'm meaning is range of the column space, right? And then what is the rank of A?
2.
So 2. And then what happened? Nullity, null space.
I think rank will be 1 only. I think so. It will be not 2.
Why? Why?
Because what I'm able to see, the rank definition somewhere I've read, ki, like when we are taking m cross n, so
Hmm?
the smallest determinant of that part, if it is 0, so the rank will be below to that. If I'm saying 2 cross 2 matrix within that, and if I'm finding the determinant of that, that comes out to be 0. I think the very first one only, 1 2 and 2 4. So if I'm finding the determinant of that, it is 0. 2 cross 2 determinant is 0. The smallest determinant, if you take in that, if it is 0, the rank will be less than that. No, Acha, at least any at least one non-zero. Okay, got it. At least one non-zero. Not all. Got
Yeah.
it. At least one. So at least one means
You
ki
can always
second.
have matrices like 1 0 0 1 and then 0 0 0 0. Again, the determinant is 0 for this and yeah,
Okay, at least one will be
fine.
0. Then it will be.
Yeah. What is the dimensionality of null space?
It's a 0.
0. Now just check the rank nullity theorem. 2 plus 0 equals to 2. This is correct. Fine. Now you can always do this for A transpose, right? For A transpose, how many column vectors are independent? Anyone?
2.
Let's see. 1, 2, 2, 4, they are really independent. And then 4, 8
2,
is
3,
also
5.
dependent. Yeah.
Yeah.
So
1, 2,
1, 2,
3,
and
5.
3, 5. 2, 2, 2, right?
Yeah.
Dimensionality of range is essentially 2. And then null space,
Then okay. So it should be 2. It
No.
should be 2.
1, 2, 3, 4, right? 4, so 2 over. It will be 2, right? And then rank apply the rank nullity. You will see that the input is 4-dimensional. Is this true?
Right. Yes.
Right. Fine. And then the options are column space of A is 2-dimensional subspace of R4. That is true. Column space of A transpose. A transpose.
So the row space of A basically.
Basically, row space of A is a 2-dimensional. Let me think. Where is A transpose? Okay. When you take A transpose, you get 1, 2, 3, 4, 5, 6, 7, 8. Now this is basically 2 cross 4. This is a 4-dimensional space, right? And the range wait a minute.
So statement 2 is false, right? Because column space of A transpose. So its size will be 2 cross 4. So it's a mapping from R4 to
4
R2.
R4 to R2, right? And we are talking about the range space, right? Okay,
Right.
yeah. We are talking about the
So it
range space, yeah.
cannot be a
Option
subspace
2
of
is wrong.
R4. Yeah.
So option 1 is true and 2 is false. Option B is correct, right? So this is how you solve the problem. So the important thing here to note is just remember the definitions. So what is this domain and what is the range space? And what is this matrix mapping A? If you care about this, then the range will be your column space or row space, right? So now for the A matrix, the domain was what? A 2-dimension, R2, right? And range was R4, 4 cross 2, right? Yeah. And for A transpose matrix, you can see the domain was R4 and the range was R2. So option 1 says column space is 2-dimensional subspace of R4. That's true. For IA transpose, it is a two-dimensional subspace of R2. Again, this has to be R2, right? This has to be R2. This is it, right? Fine. So let's continue in the next session, the problems. Fine, everyone?
Okay, sir. Thank you, sir.
Yes, sir.
Okay.
Thank you, sir.